Hello everyone, my name is David Din. I'm a sales engineer with JuliaHub, and today I'm going to talk to you about causal versus acausal modeling, specifically how the latter unlocks reusability and flexibility in system design. So here we've compiled a list of opinions and thoughts from these various sources, and here we can see some of the takeaways or opinions that people have on the causal modeling approach. So the pros of this are that it's used in many software packages today. And of course, because of this, many engineers are much more familiar with this type of approach. The downsides of using a causal modeling approach is that extending a model may require rewriting previous pieces. You encode how the model is calculated as opposed to how the model behaves at the higher level, can be less numerically stable, and generally simulates slower. Acausal modeling, on the other hand, in this list of pros, it models using a higher level description of the system and allows for the exact equations to be generated by the computer. Better numerical stability and compute performance, and better model reuse and hierarchical modeling. The downsides of acausal modeling are that it's more restrictive in the available software today in industry, and of course, because of that, it's not taught as often in American universities. Okay, so these are kind of the opinions from industry regarding the differences between these two. But what we're going to do today is we're going to do an explanation by example. Okay, so what we're actually going to do is we are going to build up an RC circuit, and we will do it from both a causal and acausal approach. And then what we'll do is we'll move on to part two, if you will, and we'll try to build up an RLC circuit. And we'll also take a causal approach to building that up and an acausal approach to building that up. And hopefully by the end of this, the differences between the two approaches are very apparent. So we'll start off by designing an RC circuit using the causal approach, right? And using the causal approach, the first thing we're going to need to do is derive causality. Okay, so what we're going to do is we start off with our fundamental equations. Here we have Kirchhoff's voltage law, which states that the sum of the voltages in any given loop should sum up to zero. We have Kirchhoff's current law, which allows us to conclude that the current going through the resistor is equivalent to the current going through the capacitor. And then we also have these device equations, right? The equation for the voltage current relationship in the resistor, otherwise known as Ohm's law, and also the current voltage relationship in the capacitor. Okay, so these four equations are a starting point. And what we're going to want to do is derive causality from these equations. In other words, what we want to do is we want to solve for the differential term here. We're going to want to solve for VC dot right here. Okay, so here are these same four equations that we just saw in the previous slide right here. And what we're going to do is we're going to rearrange these equations, ultimately ending up on what you see at the very bottom down here. Okay, so we'll start with we'll go ahead and do the derivation, which is just this middle line right here. So the first thing we want to do is find an equation for VC dot. And we do that by just rearranging this equation right here. We're just going to take this equation and divide both sides by C. Okay, divide both sides by C. And when we do that, we get this relationship right here. V dot C is equivalent to IC over C. So next, what we want to do is substitute in for this value of IC. We can substitute in IR using this relationship right here. And what we end up with is this equation right here. Then we're going to substitute in for IR. We're going to take this equation right here and divide both sides by R to get the current through the resistor is equivalent to the voltage across the resistor divided by the resistance. And doing that substitution, we end up right here. Then we're going to substitute in for VR by solving this equation right here. So we can see that VR is equivalent to V minus VC, which is the substitution we see right here. And of course, we end up with this equation. And then all we do right here is move the R to the denominator right here. Then we end up with this equation right here. The V minus VC over RC is equivalent to VC dot, which is the equation right here. Okay, so that's kind of the first thing we need to do in the causal approach. We derive causality. And the next thing we need to do is implement this equation in our simulation. So here, we're going to take a look at what this equation looks like, both in its block diagram and its code-based representation. So the framework we're using here today to demonstrate all this is the Dyad framework. Okay, so we're going to be using Dyad to show both the causal and acausal approaches. Okay, so Dyad itself is an acausal modeling framework, but because acausal modeling is a superset of causal modeling, that means we can do both acausal and causal modeling using Dyad. Okay, so that's what you're going to see here today. We're going to take a look at Dyad schematics that you see right here, and also the code representation of these Dyad models. Okay, so the equation that we derived on the previous page was this right here, right? So VC dot is equivalent to V minus VC over RC. And this is the causality that we derived when we took a look at our RC circuit. So this right here is the block diagram for this equation right down here. So let's go ahead and take a look at this block diagram and convince ourselves that this does in fact represent the RC circuit. Okay, so going into this add block right here, we have two signals going into it. We have this first signal, which is V, which is the voltage source. And then we have this second signal right here. And this second signal, this blue signal right here is negative VC. Okay, so we're just going to assume that the blue signal is negative VC right now. And by the end of this, we'll convince ourselves that that is indeed the case. But as of right now, we're just going to treat this sort of like an assumption as we walk through this block diagram. So because we have two signals entering this add block, we have V and negative VC. It follows that the signal that's coming out of the block is V minus VC. Then we see this signal enter this gain block right here, and this gain block divides everything by RC. So the signal that comes out of the gain block is, of course, V minus VC divided by RC. And of course, this term right here that we're looking at, this term right here is also equivalent to V dot C, right? So the signal that's going into this integrator block right now is V dot C. So if V dot C goes into the block, the signal that exits the block is going to be simply VC. No dot, right? It's just VC. VC dot goes in the integrator block, and then just VC comes out of the integrator block. Then we see the VC signal goes into this gain block, which multiplies everything by -1. Therefore, the signal that comes out of this block is going to be negative VC, which is indeed this value at the very beginning that we assumed. Okay, so there we have it. So this block diagram right here represents our RC circuit. And then on the right side, we see the code representation of the same block diagram, right? We have an add block right here. That's this add block. We have an integrator block, which is this. We have two gain blocks, 1, 2. And then lastly, we have the voltage source, which is this guy right over here. And then we have all these connect statements right here, which connects the inputs to the outputs of the various blocks. Okay, so this is it. This is our RC circuit model that we got by using the causal approach, right? So we started off with the voltage law, current law, and the device equations. We derived causality by solving for the differential term here, VC dot. Then we implemented this in our tool. We can see the visual block representation of this tool right there on the right side or on the left side. And we also see the code-based representation on the right side. Okay, so that is the RC circuit using the causal approach. Now let's see how we would build up an RC circuit using the acausal approach. Okay, so in an acausal approach, what we want to do is take a component-based approach. And what that means is we're going to define and create our resistor, capacitor, and inductor first as individual models or components, and then we'll connect them together to create an RC circuit. Okay, so what we do is we first start off with defining a connection right here. So we define a connector called a pin, and this pin has two variables, a potential variable called a potential variable for voltage, and then a flow variable for current. So this connector is going to allow us to connect various components to one another. Okay, so connectors allow components to be connected to one another. And at the point of these connections, we have a potential variable voltage. And because it's a potential variable, what's going to happen is the voltage is going to be equivalent at wherever these pins are connected, right? So if pin 1 is connected to pin 2, the voltage at each of those pins is going to be equivalent. Then we have a flow variable for current. And the effect of this is when we connect two components together at their pins, the sum of the current at those connections will be 0. Okay, so for example, if we connect pin 1 to pin 2, the current through pin 1 plus the current through pin 2 should equal 0. So we have a pin right there. And then next what we do is we create a partial component called one port. So the reason why this is a partial component is because we're going to use this component to build other components. In a little bit, you'll see that we use the partial component to create our capacitor, resistor, and inductors. But right over here in the one port component, we see that this one port has two pins, a positive pin and a negative pin. And the one port component has two variables, a variable for voltage and a variable for current. So this one port has a set of relations that the component will need to enforce. Okay, so here we can see that the voltage across one port is equivalent to the voltage at the positive pin minus the voltage at the negative pin. We can see the current through the one port component is equivalent to the current coming from the positive pin. And we know that the current from the positive pin plus the current from the negative pin is going to be equal to 0. Okay, so this is the one port component. Now, on the right side over here, we're going to start to define our resistor, capacitor, and inductor. So here we define a resistor component which extends one port or inherits from one port, meaning that everything that one port has, all the variables, components, and relations, the resistor will also have those same things, okay? In addition to all those things that one port provides, the resistor also has its own parameter R for resistance, and it has this relationship that must be enforced. So this is right here is the Ohm's law, right? The current voltage relationship for the resistor. So we have the the voltage across the resistor is equivalent to the current times the resistance. And similarly, we can create a capacitor component in a very similar way, right? So here we have a capacitor component which extends or inherits from one port. In addition to everything one port provides, the capacitor also has a parameter C, which represents the capacitance, and it has this voltage current relationship, which states that the capacitance times the derivative of the voltage is equivalent to the current. And then even though we're building up an RC circuit, so because we're building up an RC circuit, that's all we really need, this resistor and capacitor. But we'll go ahead and define this inductor component also, so we can use a little bit later. And this is pretty simple. It's the exact same thing, right? This is also just going to extend one port. It has its own parameter for inductance and its own voltage current relationship specific to the inductor. Okay, so there we have it. So we have this resistor, capacitor, inductor that we can use. So now how do we construct our RC circuit? On the left side over here, we see the graphical representation of the block diagram inside Dyad. And here, what we see is we have a resistor and a capacitor connected in series. And we also have a voltage source right here. This voltage source is attached to a ground component, which provides a reference voltage of 0. And then there's also a step input right here, which tells the voltage source what the voltage signal should look like. All right, so here, this is the RC circuit using the Acausal modeling approach. And what you'll notice is that this actually looks like the RC circuit, right? This is actually very intuitive. It looks like you have a resistor connected with a capacitor, connected with a voltage source, all in series, right? You can visually see that. If we look at the RC circuit that we were set out to create, this is it's almost identical, right? We have a resistor, a capacitor, and a voltage source all in series. And that is what the Acausal representation also looks like. Recall the causal representation of the RC circuit when we created this block diagram right over here. Like, right, this block diagram is not intuitive. This does not look like an RC circuit unless you're very, very familiar with working with circuits or block diagrams in general. An engineer who's not super familiar with these tools would look at this and not come to a conclusion of what this circuit is very quickly. All right, so in addition to the block diagram of the Acausal modeling approach looking a lot more intuitive like the RC circuit, the code-based representation is also equally intuitive. So we see here we have the Acausal representation of the RC circuit. What this RC circuit consists of is, of course, the resistor, a capacitor, just like expected, and then it has the voltage source and the ground and step components. Okay, so you can actually look at this and be like, yeah, I think this might actually be a RC circuit by just looking at what components that are included in here, right? We have a resistor, capacitor, voltage source. You can probably guess that this is some kind of RC circuit. And then we have all the connections right here, which are the connections you see right here. Okay, so that is how we build up the RC circuit using the Acausal modeling approach. Now, let's go ahead and move on to the RLC circuit. So basically, we want to build up something similar to this, but we want to have an inductor in series also. And the inductor is going to be placed right between the capacitor and the resistor. So we're going to build up this RLC circuit again. Not again, but we're going to build up the RLC circuit, and we're going to take the causal approach to see how that looks like. And we're also going to take the Acausal approach to see what that looks like. So here, with the RLC circuit in the causal approach, we start off similar to how we did before, right? We have Kirchhoff's voltage law right here. We have, of course, a new term in this because we have the voltage across the inductor. And then we have Kirchhoff's current law, right? So we know that the current going through each of these components is equivalent to one another. Like before, we have the resistor and capacitor device equations. And we also, in addition to those two, we have the inductor equation for the current voltage relationship there. All right. So what we're going to want to do, what we need to do here is derive causality, just like last time, right? So what we do is we start off with the four equations that we just saw on the previous page from Kirchhoff's laws and the device equations. And we need to derive causality. And in this case, what we want to do is we want to solve for the differential terms right here, VC dot and IL dot. Okay, so we're not going to go through this step by step, but you can go through this exercise of rearranging these equations. It might take you like 5 or 10 minutes. And then ultimately what you end up is with these two set of equations down here, right? We have the derivative of VC is equivalent to I over C. And then the derivative of I is equivalent to the voltage coming in minus the voltage across the capacitor minus IR over L. Okay, so the next step we need to do now that we have our causality is to implement this as a model in the block diagrams and in the code-based representations. We have these right here, and this is going to be the representation of the RLC circuit, right? So I'll walk through this a little bit quickly, just like last time, but I want to convince you that this is indeed the RLC circuit, right? Maybe you can tell by looking at it intuitively. I cannot. So what I'm going to do is just walk through this, okay? So here we have an add block, which takes in 3 signals, right? We have the voltage source signal, which is V. We have this signal right up here. This signal is going to be negative VC, which is this right here. And then we also have another signal coming down from the bottom. And this signal is going to be negative IR. So this right here. So the blue term, so the red term is obvious, right? The red term, of course, that red signal is V, but it's not obvious yet that the blue signal is negative VC or that the orange signal is negative IR. So just like last time, what we're going to do is we're just going to assume those to be true right now. And then we'll convince ourselves by the end of walking through this block diagram that the blue signal is indeed negative VC and that the orange signal is indeed negative IR. So the signal that's coming out of this add block right here is going to be the sum of those three things that came that were inputted into it, and that's of course this right here. Okay, so V in from the source minus VC minus IR, and then the next thing is that this signal goes into this gain block, which divides everything by L. So the signal that you get coming out of this gain block is this right here. And this right here, of course, is also equivalent to what's on the left side of the equality. So this signal is also known as I dot, right? We have I dot right here going into this integrator. So if you send in I dot into the integrator, what's the signal that you get coming out of it? So that's going to be, of course, simply just I. So we have I right here and I also going down right here. All right. So what comes out of the integrator is I, and I is going to travel to the upper branch, and it's also going to travel along the lower branch. Okay. So let's go ahead and just focus on the lower branch first. So if we have I coming this direction, we can see that I goes into this gain block, which multiplies everything by negative R. Therefore, the value that comes out of this is negative IR, which is this right here. Okay, so that's one of the two assumptions we made in the very beginning. Now we believe that this is indeed the case, right? This red signal right here is negative IR. All right, now let's travel along this upper branch right over here. And then we also have I going this direction, right? This is also I. And then we see I traveling through this gain block right here, which divides everything by negative 1 over C. So what comes out of this block is going to be negative I divided by C. Well, negative I divided by C, what is that equal to? Using this equality right here, we can see that negative I divided by C is actually just negative VC dot, right? So equals negative VC dot, right? So negative VC dot is this red signal right here going into the integrator. All right, so if negative VC dot goes into this integrator, well, what comes out of it is simply negative VC, right? You send in negative VC dot to the integrator. On the other side, you get negative VC. And that, of course, is this value right here, which is the second assumption that we made when we began this. Okay, so there we have it. We convinced ourselves that this block diagram right here does indeed represent the RLC model. What's very notable, in addition to this just not being intuitive at all, like right, if I were to look at this, I would never know that this is the RLC circuit. But in addition to it not being intuitive, if we look at the previous implementation of the RC circuit, this is what the implementation looked like, right? They don't look similar at all. Like the RC circuit does not look similar to the RLC circuit in their block representations. And what that means is it's very hard to reuse this, right? Like you've done all this work to create an RC circuit, and now you want to go, okay, well, maybe I want to design an RLC circuit, right? But you have to start from scratch and derive all the equations from scratch to build up the block diagram from the very beginning. You're not able to really reuse the work that you did when you constructed the RC circuit. When you go to the RLC circuit, you need to start over and do your work over again. And then on the right side over here, we also have the code-based representation of the RLC circuit. Okay, so we see here, I'm not going to walk through everything here, but right, we have, actually I will, it will be quick. So we have the voltage source right here. We have the gain block or the add block right here. We have 3 different gain blocks here, here, and here, and then 2 integrators here and here. And then we also have, oops, pardon me. We also have these connections which connect all these blocks together. So that is the causal approach for building up the RLC circuit, right? We needed to start from our equations at the very beginning, work from there to derive causality and solve for the differential terms. And then we were able to construct the block diagram for this model. Okay, so how does the RLC circuit look like if we take the Acausal approach to building up the RLC circuit? Okay, so to do that in the Acausal workflow, we actually are able to reuse everything we created before, right? Before we created this pin, this 1 port, and we implemented this resistor, capacitor, and inductor. So we don't actually have to do anything new here. We can reuse all these components that we built up earlier, okay? So how do we use these to build up the RLC circuit? We have a inductor in between a resistor and a capacitor. That's what we said that we needed. And there it is. We simply just put the inductor into our block diagram in between the resistor and capacitor and make the appropriate connections. And if you look at this, once again, this is very intuitive that this is an RLC circuit, right? You see the resistor, the inductor, the capacitor, and the voltage source, right? This looks very similar to an RLC circuit, right? You have a resistor, inductor, capacitor, and a voltage source all in series. So it looks very, very similar or intuitive in the Acausal representation of the RLC circuit. And for the code-based representation of the RLC circuit, the only differences here from our previous RC circuit are what's highlighted. We added this inductor, which is right here, and then we created these two new connect statements to connect the resistors to the inductor and the inductor to the capacitor. And that's it. That's all we had to do. We just had to add in those terms to go from an RC circuit to an RLC circuit, okay? So in summary, what happened as we went from modeling an RC circuit to modeling an RLC circuit? How did one model evolve into the next? Well, for the most part, in the causal approach, one model did not evolve into the other one, right? We had to build up this model, the RC model, and then when we moved on to the RLC model, we couldn't really evolve or build on top of this at all. We had to start from scratch and rederive the equations and rebuild the block diagram, okay? And similarly, if you look at the code representations for the causal models, when you go from one model to the next, it's not very intuitive that this is the RC circuit and that this is the RLC circuit, right? And even if you know this is the RC circuit, it's not very intuitive looking at the code like, hey, what other pieces, what other components do I need to include into here? And what connections do I need to make, right? Because understanding these code-based representations can be just as non-intuitive as trying to understand these block graphical-based representations. Okay, so this is the causal approach. And how did the model evolve in the Acausal approach, right? So in the Acausal approach, we started with this for our RLC circuit. And when we wanted to incorporate or build an RLC circuit, the only thing we had to do was add this inductor right here. That's all we had to do. We just had to put this into our previous model and we're good to go. We're able to reuse everything we previously did. And then the code-based representations of the Acausal models are equally as intuitive, right? In the RC version, we started off with a resistor and a capacitor. When we moved to the RLC circuit over here, all we had to do is add in an inductor because, you know, an RLC has an inductor versus an RC. So all you do is add an inductor and then you add the connect statements to connect everything in series. And that's all you need to do. You don't have to rederive anything. You're able to reuse everything you previously created. So I hope that demonstrates or illustrates the difference between these two approaches and how much work and time you can save by taking the Acausal framework as opposed to the causal framework. So in summary, compared to traditional causal modeling workflows, the Acausal modeling approach enabled by Dyad is easier to read, it's easier to debug, to extend, and to model larger systems. We saw how easy it was to read and debug as we looked at the block and the code-based representations of these models. We saw how easy it was to extend our RC model to build an RLC model. And of course, that makes it easier to model larger and more complex systems. So if what I recommend everyone do from this part on, the next step, I recommend you go to this link right here to get started with Dyad, so you can start exploring this framework and how you can do Acausal modeling within it. If you have any questions, please feel free to contact either us at JuliaHub, or you can email me directly, and we can start the conversation from there. All right, thanks for everyone for joining. Have a great day.